Hey everybody, this video is going to give you a little insight into the expectations and an example of what your next project is going to be. The basic idea is you are going to be responsible for finding a video or a cartoon and finding a clip from that, and then going through and analyzing and discussing the physics behind it. Does the video or the cartoon accurately represent the physics? Why or why not? And explain that to your peers. That's the plan, and this video then will be the example involving WALL-E and his fire extinguisher scene. Enjoy! And now the scene from WALL-E that we're going to be analyzing. Now I'm going to show a little bit of lead-in and a little more of a context of where this little portion of the clip is coming from. But what we're really focusing in on is the fire extinguisher scene. So keep in mind, WALL-E's in the middle of outer space, and he's using a fire extinguisher and in order to apply a force on him. So that's going to be the part we're going to watch and focus in on, but this is going to be the clip that kind of leads into that piece. So here comes WALL-E with his fire extinguisher, and our actual scene of interest is going to start right about here. This is actually phase 1 of the motion. And then phase 2 is when he turns on the fire extinguisher. So once again, when we're watching this, if we want to zoom on back, yay for rewind. Okay, so if we watch this now, we have right here, this is going to be our phase 1. So this is phase 1 of our motion. And then we keep on going. So this is phase 1 from here until right there. And then, let me kind of zoom back again. I'll show you exactly where it is. So we have phase 1 from there to about there. And then at this point, when he turns on the fire extinguisher, this is going to be our phase 2 part. So phase 2 looks like this. Now, in order to understand WALL-E's motion, be able to analyze it from a physical standpoint, we need to understand what forces were applied on WALL-E. And we know that when he turned on the fire extinguisher, it caused him to change his motion. So in order to understand this, we need to figure out how does the fire extinguisher affect the motion of WALL-E and why. So in order to do that, let's think of a balloon first, and then we'll show the parallels in just a little bit. First thing I want to think about is when we have a balloon and we blow it up. So we're blowing up our balloon, and when we do that, we see it's expanding. And it's expanding because you're putting air into the balloon. That air pushes outward on the material of the balloon, and you get this outward force applied on our balloon. So from a physics standpoint, this is all the outward force of the balloon. So force of the air on the balloon. So the air is pushing outward, causing that balloon to expand. Now, in order to make this a little bit more simplistic, and let's first of all kind of look at what's happening over on this end. When you look at this exterior portion of the balloon, you can see that over here, there's this opening. This is the opening where all the air would come out, okay? And you can see that there's no force, there's no balloon for the actual air to be pushing on. Instead, it just escapes outward. So now I want to simplify this just a little bit. So let me get rid of some of these extra forces, and let's just look at the vertical and horizontal pieces. So, vertically speaking, we see that we have two forces. This is a force of the air on the balloon, and another force of the air on the balloon. One's pointing upward, one's pointing downward, at pretty much the same force value, same magnitude, in other words. So as a result, these two forces pretty much cancel out. In other words, they're balanced in the vertical direction. Now let's look at this horizontally, though. Horizontally, we have this force over here, the force of the air on the balloon, but on this outside end over here, there's no air no balloon for the air to push on, so we're left then with an unbalanced set of forces. We have the situation where this force is causing my balloon to have a net force in that positive direction. That's causing then my balloon to accelerate, to move, which is the whole idea of Newton's laws of motion. Whenever you have a net force on an object, it's going to cause it to accelerate. So my balloon is going to be accelerating in that rightward direction. So now let's connect this up to a fire extinguisher. You get the same kind of idea. You have, when you point the fire extinguisher to the left, and all the junk from inside that balloon, inside the fire extinguisher, is pointing out and being spewed out to the left. This is very similar in nature to the air balloon, or the balloon, the air in the balloon. The air in the balloon is getting pushed out to the left, just like the stuff in the fire extinguisher. As a result of that, in the balloon, it caused that force going towards the right, and it's going to be the same for my fire extinguisher. I'm going to have a net force, or the sum of my forces, is going to be pointing away from where all the junk is getting spewed out of. So now, let's see if we can use this idea to figure out if we have this force pointing in this direction, this force pointing over in that rightward direction, that positive direction. How is that going to cause my balloon to move? So now, here we have this balloon. You can see over here on this end is where the air is going to come out. It's all blown up. It's on a little zip line that goes across the room, and it's on a little straw, so it's all attached. Now the question then is, with the same setup, with this balloon, with all the stuff, all the air coming out of this end of the balloon, what's going to happen to the balloon when it's released? When that air then is able to push it forward? In other words, how are the forces going to affect the motion? So here we go. Let's watch our video real quick. So what we see when we do this then is exactly what you maybe would expect from your own experiences, is this idea that when your balloon is over here, when all your junk is going to be coming out, in other words, air in this case for the balloon, is coming out of this back end, that's going to cause the balloon to be moving forward. In other words, once again, the force on the balloon is in that direction, in that positive direction, and as a result, since it's at rest originally, that force is going to cause the balloon to also move in that same direction. Same thing with the fire extinguisher. Think of it this way. This end of the fire extinguisher is the hose that's going to be pointing out this way. Okay, the hose is going to be pointing this way, causing all the junk from the fire extinguisher to be pushing, or to be forced out that way. But the actual force on the fire extinguisher is in the opposite direction. And that's exactly what happened with WALL-E. So we're going to use this foundation then to analyze the videos from WALL-E. So now we want to look at phase one. Phase one of WALL-E's motion. Here's the little video clip of it again. As you can see, he's moving across the screen in outer space. There's no fire extinguisher on. So no fire extinguisher on means he's not applying a force to that and using the fire extinguisher. Because he's in the middle of outer space, there's no gravitational force. There's nothing else pulling or pushing on him. So literally his free body diagram is just this, just WALL-E. And as we know from Newton's first law of motion, if there are no objects acting on the, or no forces acting on the object, so the net force on the object is equal to 0. So our way of representing that mathematically is that the sum of the forces is equal to 0 newtons. If that's a fact, and that's the situation, then we know that our object is going to stay in motion, which means it's going to be staying at a constant velocity. And as you can see up here in that video, let me see if I can play it again. You can see WALL-E's moving to the right at a constant velocity. So moving to the right at a constant velocity, nothing's causing him to speed up, nothing causing him to slow down at all. So therefore, yay, Pixar got it right. And now we're looking at phase two of this motion. What you can see up here in the image, over in this region, with the fire extinguisher, is that the fire extinguisher hose is pointing this way. So the hose is pointing to the right. That means that he's going to have a force applied to him in the opposite direction. So there's going to be a force pointing over here towards the left. Now this is where it gets a little more interesting. So we have over here a force, this is my free body diagram, the force of the fire extinguisher on WALL-E. Now because of the fact that WALL-E's moving to the right, while he's applying a force to the left, this is going to mean that in the first part he's going to be slowing down. Well, we know he's not going very fast, so then as a result, what we're going to get is he's going to be moving to the right, slowing down, and then before we know it, he's actually going to no longer be heading to the right, come to rest, and then very quickly be moving to the left and speeding up. So that force is going to cause him to slow down in the positive direction, change direction, and speed up to the left. At least in theory, that's what we would expect using Newton's laws of motion. So let's see if that actually is what happens on here as we analyze this video. Sure enough, let's watch it again. He points his fire extinguisher to the left, causing him to apply a force to the right. And you can see that for one brief instant of time, he slows down and then speeds up in the opposite direction. So once again, Pixar did what they were supposed to do. They analyzed this, it worked out, and Newton's laws of motion did come through in WALL-E. Thanks for watching, and this is what I'm hoping you guys can do with your own favorite scene from a certain movie, from a cartoon. Tell me about the forces, tell me about the motion, tell me about friction. Does it work? Does the physics behind these kinds of ideas, these kind of clips, are they actually being shown in what? And our ultimate goal is to figure out, was physics used properly? So that's your task, that's your goal, and I'm excited to see what you guys come up with.